Log on, tune in, find out. Another good idea from Cambridge.
Okay, so I'm very pleased and honored to have the opportunity to speak to you all today. I'm going to speak about development of wavelet methodology for weather data assimilation. I think that's what everybody in the room understands enough of those terms to not need any explanation initially, or at all really. My co-author is Thomas Olignier, also at NCAR and M-Cubed, and formerly from the ECMWF. This is an area I've worked in only for about a year, although I've been working on wavelet methods in different respects for considerably longer than that, always at NCAR. And so the outline is, I'll briefly summarize the purpose of this talk, or of this research, which is to achieve a joint scale and location localization of covariance. And then I'll also give you some background about wavelet analysis of nonlinear multiscale structures, because of the success of wavelets in other areas is really the motive to try them in this area. Excuse me. Then in the second part of the talk, I'll present my analysis and modeling methods. I'll present a slightly different kind of wavelet analysis than you may have seen before, called the horizontal two-dimensional isometric injective wavelet analysis. Isometric only means that it conserves the sum of squares, and injective just means that it's left invertible but not right invertible. Then I have a model for the background error covariance, and then that model is based on some work by colleagues at Météo France and elsewhere, by parameterizing covariance in a certain way, which I'll explain. And then some more innovative work is on using wavelets to estimate the representativeness error, which I'll also discuss. I do have some initial results, maps of variance which are generated by this model and compared with more common variance estimates. I'll show you some pseudo-single observation tests, which are basically rows of the covariance matrix where a certain row corresponds to a certain point in space, and then some simulations of representativeness error. I'm very happy to be interrupted at any time, and such a small group, and I know just about everybody, please feel very relaxed to interrupt me. So starting now with the purpose of this research. So the numerical weather prediction simulations and observations are increasing in spatiotemporal resolution and complexity. This is, I'm showing an uncontroversial statement. We have just more complex models, higher resolution, and more observations. And so since the atmosphere contains strongly nonlinear multiscale structures, the simulations and the observations are capturing those, and we need to deal with them, which is the next sentence. So data assimilation has to represent and compute those structures. Enabling the background covariance to be scale selective and location dependent should greatly improve the overall model flow dependence. So that's a little bit of jargon, but basically there's so much information that you need some mechanism for selecting scales which are important, and doing so where in physical space it's important to do so. That's the location dependence. And then depending on the situation in the weather prediction, you want to also adapt to that, and so that's called flow dependence. So these are the long-term purposes, and because wavelets have been useful for such purposes in other areas, we hope they'll be useful here. I just want to briefly mention this work has been inspired to a large extent by work by other authors and at various, mostly European, entirely European locations. and some meetings in England. So the background that I bring to this is my familiarity with, this, as I said, the wavelet analysis for similar types of problems. So this result goes back to 1991. If we consider a spatial covariance, which I express this way as some kind of ensemble average of dependent variables x, which are located at space points R, such functions which depend on 2 points, and if we can trust that the function decays as a function of point separation no more slowly than a certain estimate, then there's a guarantee, that is a theorem, that you will get a sparse wavelet matrix representation. So if m and n are my indexes of both the variables and the points, I could have multivariables and multiple grids. Then, sorry, I lost my train of thought. That's a matrix of very large dimension because of the very large grids in 3 dimensions, say. And so, but if I know that as a function of point separation, it's very smooth, then the wavelet matrix representation will be very sparse. And so there'll be a factor of order n log n and asymptotically order n, significant entries, that is, above a fixed threshold of magnitude, per coordinate discretized to n points. So A is just labeling my direction, and this could be 1, 2, or 3 directions. The work I'm talking about today will be 2-dimensional, but that's not a real limit. There is something called the curse of dimensionality I want to mention very briefly. So for example, matrix multiplication costs n cubed per dimension. So the product of the n cubed factors in each dimension. But when you have a sparse representation of this form, then matrix multiplication only costs a factor n for each dimension. And then recent works by Belkin and Molenkamp, again for a certain class of operators, can reduce that cost from the product down to the sum of order n. So there really are very fast methods for linear algebra coming from these kinds of approaches. Again, that's a motive we haven't, in the work I'll present, we haven't implemented such fast methods yet. Also, in regard to covariance, there is an established record for wavelet-based representation of covariance. So for example, this is from 1994, so it's pretty small, 143-member ensemble of 128 squared pixels of face images, and then so-called best basis wavelets, which I reviewed in 2000, can represent 90% of the variance with 2% of the coefficients. And if you think that's good, there's an approach called wavelet approximated Karhunen-Loew analysis, which more commonly known in our field as empirical orthogonal functions. And that method achieves 88% of the variance on only 0.06% of the coefficients. And that's reviewed by Wickerhauser, 1994. I'll give all the references at the end of the talk. Please.
Is that at all for surface fields, like surface temperature fields, something like that, some response from?
Yeah, let me show. I don't think I have an analysis of such fields. I have some work in some of my papers. I'm going to show you a simulated field that might satisfy your curiosity about that, or at least make you imagine it would work. I'm very confident it would work.
So I don't mean whether it would work, but just what sense of reduction you would expect to be able to capture.
Ask me after the next slide if it still seems like a good question. If it still doesn't seem suggestive. Thank you. So here I'm plotting the wavelet coefficient magnitude. So I have an x tilde, which is my wavelet coefficient, and then the wavelet index is I, but I'm going to re-index it by a rank S. So that's sorting on the magnitude, and I'm going to plot that versus S, and I'm going to normalize it by the L2 norm squared, basically. So that's this quantity on a log-log plot. And I'm going to do some test functions in which my spatial function is x of r in 2D. I'm going to compute its Fourier coefficients x hat, and I'm going to simulate that by putting in what amounts to a power law. So I have this form for the basically the magnitude of the wavelet coefficient, and then the Fourier coefficient. Then I give that a random phase, and then because it's 2D, this expression in the bottom, which is 1 plus c to the 1 plus b, would amount to a power law of c to the negative b because of the metric term. Okay, so basically a power law in Fourier space. So for different values of b, I'm basically creating a field of different roughness. And then as b increases 1, 2, 3, I'm getting smoother and smoother fields, and so the wavelet coefficients are going to decay more quickly, which is the next statement. And so this is just sort of verifying what you could imagine, and if that wasn't convincing, nothing's better than a picture. So these are maps of synthetic fields for those 3 different values of b, 1, 2, and 3 being, again, the exponents in a 2-dimensional Fourier spectrum with random phases. Excuse me. And then if I reconstruct sort of arbitrarily using the largest square root of n1 and 2, which is about 0.2% of the coefficients. This is just a demonstration, so I just thresholded arbitrarily. Those coefficients represent a 44% or 91% or 99% of the spatial variance, that is, again, the L2 norm, as b increases. So even for a very rough field such as this, I get 44% of the variance. I don't really reconstruct the field satisfactorily, but there are some hot spots corresponding to those in the original field. B equals 1 is a very rough field, as you can see. B equals 2, I would say, is more like a cloudiness type field. And I would say, 91% with 0.2% of the coefficients and a lot of familiar structures comparing the reconstruction with the original is suggestive that this is worthwhile. And then B equals 3 is this one. And again, just more strong statement that or more strong observation that the reconstruction is quite faithful, and I'm getting 99% of the spatial variance. So I'm hoping that kind of suggests what we might get for a meteorological field. Chris?
Can we go back to the setup a little bit?
Mm-hmm.
We're always talking about a scalar field on the whole of R2.
Periodic, biperiodic scalar field.
Okay, so you essentially think of it as a box.
Yeah. And this is just a common test function. This is very similar to a initial state for turbulent simulations suggested by McWilliams. So I like it because it looks a little bit challenging compared to other kinds of data you might just grab.
I guess I just don't know this area. We're
Mm-hmm.
not looking at it at all. But so what is it when you take the difference between Rn and Rm? It seems like that would be periodic.
Right. So I'm only showing compression of the field. So thank you for letting me clarify that. It'll become more clear as I get into the wavelet, the covariance model. There's an issue of compressing the field, which I've just shown, and then the issue of representing the covariance has to do with 2 points. Right now I'm doing just a 1-point compression, just compressing a function. Compressing the covariance you'll see in the next section. But as far as what distance means, the actual application will be in a limited area model, and distance will just be the normal kind of distance. For periodic cases, distance corresponds to a distance on the torus without a metric. So it's just, but that's worth clarifying. Okay, so now I've got about 4 slides which are a bit technical on just sort of the equations of wavelet analysis, and I'll try to inject some interpretation to make it worthwhile. But I do want to talk a bit about just how it works and what it is. So isometric injective wavelet analysis in 1 dimension, for simplicity, transforms a sequence xn, which are values of the function x at points Rn. I have n of those function values, and I have a uniform grid Rn. I'm going to inject it into a sequence n tilde, which is larger than n, of scaling function and wavelet coefficients. And it's just a matrix multiplied by this wavelet transform matrix. Now, I need the n tilde, as I'll say in a moment, because if I don't want to assume any boundary conditions, and if I don't want to limit myself to a power of 2 in my data length, which are very inconvenient, then this method allows that. So the inverse wavelet transform is, again, a linear transformation with a W check, which could be a different matrix. In the work today, it will be the same matrix, but it need not be. And then isometric means, as I said, the sum of squares is the same. And as I said, the wavelets here eliminate the usual severe restriction that we have to have a power of 2 of points. So one slide about what wavelets mean in terms of how are they indexed. How are they indexed is the briefest way to say what information they contain. So the index n I've been using describes spatial location from n equals 1 in the west to n equals 1, a large number in the east. The index I, which I'll use for the wavelets, falls into intervals which I label by L. So the beginning of the interval is always I bar L, and then the length of the interval is I check L. And the index describes both the wave number band center and the bandwidth. And those will be proportional to I check at level L. But the index also describes spatial location proportional to I minus I bar L, so starting at 0, and then dividing by I check L. So the index, as you'll see in the pictures later on, combines those 2 kinds of information in one. So just some formulas. This is not so important. It's just for completeness that we have a formula for IL, I check L, and I bar L. Basically, I check L, this is just a recursion which generates a so-called dyadic partition. If I start with I0 being my data length, then I do a recursion to get all these different IL lengths. And then my I check out, these are basically the lengths of low-pass filter outputs. And then this I check L is the length of high-pass filter outputs. And the I check L's correspond, as I said, to this meaning of band center and bandwidth. And then the I bar L is just this expression, which gives me basically a pointer to where in the decomposition I am. So L is the total number of levels. Little L says which level I'm on, going from small scale to large scale. And then the 2 P's are just the lengths of the filters. Notice that there's a floor function here. So if I had a power of 2, then, if I had a power of 2 and I assumed periodicity, then these P's would go away and the floor function could go away, and all the I's would just be powers of 2. But in order to avoid those assumptions, we include the filter length and we include the floor function, and then we have much more flexibility, only at the cost of complexity. I wanted to mention, because I have a space to stick it in, that the smoothness of the original function is precisely characterized by the collection of wavelet coefficients. So if it's the smoothness at a point r, then when this expression is near r, that contains the information about how smooth that is, i.e. how differentiable it is. In fact, what the Holder exponent is can be derived from these coefficients. Okay, so just to show you what a wavelet looks like, if I take my wavelet coefficients to be Kronecker deltas at certain values, then I'm going to take P and P check to be the same. If I use a short filter, 6, I get this blue wavelet, which has some interesting cusp features. If I let those filter lengths be larger, like 30, then I get a smoother wavelet. You might see in some of the plot labels later reference to either a C6 or a C30. Excuse me. The C refers to Koifman because he suggested a certain kind of approach which made the wavelet almost symmetric and gave vanishing moments. Vanishing moments just has to do with thinking of the wavelet as a distribution, which can be positive or negative, and then the moments of that distribution, the more of those vanish, basically the more orthogonal to a polynomial, or the higher degree polynomial is the wavelet orthogonal to. And that means that if you have data which behaves like a polynomial in certain regions, the wavelet coefficients will be extremely small. And that underlies why wavelet compression works. Because typically in actual meteorological fields, the areas where it doesn't behave like a polynomial are localized.
I'm used to the idea of wavelets where you start with another wavelet
Mm-hmm.
and you do this translation and compression and stuff.
Right.
Does
That still fits in.
fits in here?
Yeah. That introduction to wavelets is always assuming the entire infinite line. And then when you actually have boundaries to deal with, you can't do that dilation operation at some point you hit the boundary.
But you could do it on doubly periodic domain.
Not without change. The recursion no longer holds because the recursion works when you don't see the boundary, and when you're near the boundary, the recursion is actually broken. So they have to be periodized. So in that Fournier 2000 paper I cite, it's explained how that works, and it's also in Dalbashi's book, but it's way in the back. So you may not have got to it. But yeah, it's basically these wavelets, if they're away from the boundary, they obey that recursion relationship. But near the boundary, you need to do some things. And then, again, I've also taken care of the fact that we're not going to use grids that are a power of 2. So it's everything you know plus some stuff. Thanks for the question. So speaking of recursion, I'm going to show sort of the hierarchical structure of wavelets quickly. In matrix form, I can say that my wavelet coefficient as a row vector is this matrix multiplication by a row vector, of a row vector by W matrix. Or my inverse, X, is a column, which is a matrix times a column of wavelet coefficients. And that computation is actually a sparse recursive hierarchy. So what does that mean? So let's consider the case of the wavelet coefficients. I'm going to row multiply the data by this matrix. So what is that? This bracket notation just stands for concatenation, putting columns next to each other. And so the detail matrix is this D1 at the finest scale. And so once the details at the finest scale are computed, they're not touched again. But then the C1, the coarse transform at the finest scale, is then hit with another matrix which has a D2, which is the details at the next finest scale, and a C2, which is the coarse at the next finest scale. And then that is recursive down to the coarsest scale, L, where the coarsest details and coarsening is done. So that's the form of the wavelet transform as a matrix. And if you've ever seen a wavelet paper or textbook which shows a tree for the wavelet transform, you can think of this as the tree. this would be the first branch. Every comma would be a branch in the tree. And then that branch stops, and then this bracket is the next set of it's a tree bifurcating basically down to the course's scale would be the top of the tree. So that's just the form of it. Now I say it's sparse because the coarse and detail matrices C and D are sparse. They only contain basically a convolution with filters H or H check, which are just those sequences of length P, or P check, that I talked about before. So none of these matrices is ever constructed. It's just representing what the algorithm is. The actual algorithm is merely to convolve with these little matrices everywhere. And the L's everywhere only are labels because the matrices have different sizes corresponding to that dyadic partition. Also, I wanted to say if you multiply the C's and D's all together, then you actually get the wavelets functions, which are discretely represented as the columns of the wavelet transform matrix. So the W columns are the wavelets, and the V columns are the scaling functions. And scaling functions corresponding to low pass transformation, and wavelets corresponding to high pass. The coarse and detail matrices satisfy a certain orthogonality expressed here. So the product of C and the product of D's give the identity, and C and D are orthogonal to each other. And so by plugging that relationship into this expression at all levels, I get that W check is the identity. Notice I'm putting transposes on the left just because I need the label on the right. So this is the injection property that I have a left inverse for the wavelet transform. Or written this way, it's the right inverse. But either way, I only have this. I don't have the I don't have the identity when I switch the order of those factors. That was all 1D. I'm going to be showing 2D results, but in D dimensions, then I would have just a tensor product of the transforms in each of the dimensions alone. Okay, that was all the wavelet technical stuff. Was there anything not understood and desired to be understood? So now I'll just talk about the covariance model itself. So quickly reviewing the idea of cost function. The background part of the cost function as a function of the difference x between model and background states, or as a function of the control variable, v, is this expression. So JB, the background cost, is x transpose B inverse x, and that'll be approximately equal to V transpose V. Excuse me. So B is the background error covariance. So in other talks, such as Chris's, there was some history about where this expression comes from, which I'm not reviewing. But that's the expression we need to deal with and need to have a model for this B matrix. In meteorology, X is going to have a dimension like 10 million or 100 million, depending on which weather center you're at. And B, therefore, in its fullness, could never be represented. And so we need some fast way to deal with it. So I'm just going to give the simplest, really the simplest way we could address this using wavelets. So the usual approach for variational minimization of this JB, or actually JB plus the observation, which I'm not talking about, is to introduce a U matrix which transforms from the control variable to the actual model background difference. So by introducing U and requiring this approximation here, I get that B is approximately U transpose. So here's how we accomplish that. We're going to define U to be P inverse W check sigma. What is that? P is just an arbitrary factor. which I'll exploit. Sigma will be a diagonal matrix of all the variances of the wavelet coefficients. So basically the variances in wavelet coordinates. And x tilde now will be the wavelet transform of px. So my arbitrary p appears as an inverse on this side and as a forward operation here, and therefore it'll cancel out in the next line. So the proof is that UU transpose, if I plug in the definition of U, I get P inverse W check sigma squared, etc. Now, it turns out, this is an empirical result, I believe there's also some theoretical basis for it, that the diagonal in wavelet space is a pretty good approximation for the full covariance in wavelet space. To the extent that's true, I can assume that, and then I get that the W check factors inverse transform me back to my true covariance. So the idea is, again, is to assume diagonality in wavelet coordinates, and then as you'll see when we come back to physical space, we actually capture some covariance between points because of all those wavelet properties. Okay, as a corollary, I always want to say coronary, but anyway. As a corollary, the expression for JB, if I plug in the definition of U, of V and U, I get this expression. If I choose my control variable to be in the column space of U transpose, then this expression collapses to V transpose V, which is what I want. Okay, now P I said is arbitrary. In practice, we choose it to be a diagonal matrix of normalizing by the variance in physical space, and if I include a factor of the area at the points, then that's a useful P matrix. Any questions about the covariance model? Okay, the other idea that we're working on is to somehow use wavelets to estimate representativeness error. So now we're going to think about observations a little bit. We have an observation, y, and we have a model prediction of it, which I'll call xi. I forgot that I used xi for wave number, but anyway. Unrelated to wave number, xi is the transform of x by h, which is a so-called observation matrix. And then we're going to use the coefficients y tilde and xi tilde to find a representative basis of y minus xi. So the problem generally is that the differences y minus xi could include some model error or some resolution error or something which isn't really observations minus, prediction, which is what we want it to be. So I'm going to, again, do sorting. I'm going to say y tilde of indexed by I1 and xi tilde indexed by I2. And those will be sorted by rank S. Those are the S largest magnitude coefficients. And then S goes from 1 up to the total size. This should be an n tilde, by the way. And then because of the properties of wavelets that I've been talking about, those are also the S fewest values representing the greatest contribution to the spatial variance. Now we need to choose thresholds. There's many ways to choose thresholds. It's really an art. I'm going to introduce a new way, which I'll give you the formula for, and then I'll show you a picture later that kind of motivates it. Basically, I'm going to have thresholds tau 1 on y and tau 2 on xi, and I'm going to require significant logarithmic curve separation. That's because it's the logarithm of the wavelet coefficients that expresses that compression that I showed very early in the talk. And so I have a capital Y, which represents the log of the ratio, which of course is the difference of the logs. And then I'm going to compare the magnitude of Y to its running mean, running root mean square. And then when there's an S star such that all greater all smaller values of the wavelet coefficients satisfy this inequality, basically I'm going to show you that that's significant separation between the logarithmic curves. So basically, when the observations and the data are decaying significantly differently in wavelet space, I will argue that difference is the unrepresentative difference. If you will buy that, then what I'll do is reconstruct representative values, y star and c star, by masking the coefficients which are below those thresholds. And you'll see an example. Masking just means setting them to 0. Okay, so that was all the theory stuff, and now I just have maybe 6 slides or so of results to hopefully make it seem like it was worthwhile. So the result also found by Deckman and Baer and others is that this B model is better at representing heterogeneity. So I'm starting with, on the left, a map of the true unbalanced temperature variance. So that's capital sigma squared is the diagonal of the B matrix. It's also the variance of the T prime unbalanced. I want to map that versus longitude R1 and latitude R2, and I just contoured it. So I get some structures. This is a certain domain between roughly 90 something west and 110 west, and it's Colorado would be here. This domain for this simulation done by our colleague David Dowell at M3 has a bunch of structures in this field. So the next center picture is the wavelet wavelet variance. So it's the diagonal of the covariance. If I choose P equals I, the identity, and then, as you might guess, if I choose P, if I choose P as I said, normalizing in physical space, then I get this map. And so if you've been studying this for the last minute, you can see a lot of the structures that were in the true variance are captured more or less accurately using that P normalization. That is P equals sigma, and not so well if I don't have that. Basically, without that normalization, I get a lot more of the kind of tensor product artifacts, and the scales are wrong. And you could think of this as assuming diagonality either of the wavelet variance or of the wavelet autocorrelation. So because correlation is between plus and minus 1, the wavelets do a better job. And then when I transform back to physical space, I just put the variances back in.
Well, so in the right-hand diagram, you capture the variation of the total variance in the preconditioner. It doesn't actually matter what we've done inside that, because you can use any sort of spatial transform to still reproduce that correctly.
There was an if in there, so I'm not sure exactly what the statement is.
Well, you've captured your spatial variation of the variances in your P matrix in the right-hand picture.
Right.
And therefore it's essentially reproduced exactly, whatever sort of wavelets you've used to do the rest of the transform, but effectively reproduce the correlation structures work better.
Right, but different. So yeah, so I do have plots on the laptop I could show you of this same exercise for different kinds of wavelets, and it does give slightly different results, and that does have to do with the vanishing moments.
I was thinking that it's not, given that you've used the preconditioner, you need to look at different diagnostics to see how well the wavelets have performed.
I definitely need different diagnostics, and I'd like more suggestions in that direction. I'm just going sort of through the easiest to the less easy diagnostics. So the next thing is a pseudo single observation test. So now I'm doing the covariance corresponding to an observation single observation corresponds to the row of the B matrix, and so each row corresponds to a point. So now if I have an observation at a certain place, I have an observation at 100 west, 35 north, at a certain level in the model. I'll put an observation of 1, 1 plus or minus 1 Kelvin, and then I see what the algorithm, the entire J minimization algorithm will return this analysis, and that corresponds to a picture of the row of the B matrix. And so this is a very horizontally high resolution data set, 351 by 451. The simulation was originally with 35 levels, but I reduced it to 5 for this exercise, so it would run on my laptop.
So the left-hand picture is from a large ensemble, which gives you the truth. Which
Right.
That's right. So you're
That's right.
trying to match that.
Right. Thank you. So yeah, as Mike noticed, the left side is an ensemble approach, so no explicit B matrix, just finding the response using ensemble methods, the hybrid method actually from Dale Barker. Hybrid with everything done in the ensemble side. And then the recursive filters is what the M-cubed Whorf model uses as a default today, which is very homogeneous. And so wavelets give us something in between, localized like the recursive filters, but including some diagonal structures. So for example, you could say there are multi-scale anisotropic features such as southwest, northeast structures over North Texas. I'm talking about these, and the wavelets are capturing some of that. If I move the observation point northward at the same longitude, I get this picture. So again, there's some representation of the elongated structure, which the recursive filters don't find. I just stuck it in here that the wavelet B matrix is, again, only costs order of the horizontal dimension. It wasn't explicit that I'm not doing anything in the vertical coordinate. There's another factor of the U transform in the vertical. I'm leaving that alone, but I'm replacing the horizontal transform. If I move the observation westward now, I'm up against the Front Range in Colorado. The ensemble method gives a lot of structures, some of which...
Is that ensemble, I mean, practical application of ensemble method, you only have a small ensemble, so there are issues with that.
Yep.
Inside the ensemble, but if you're just trying to represent the truth, you can take a massively large ensemble. So is this a small ensemble or a large ensemble?
30 members.
So it's not really truth.
Right.
So it's sort of,
Did I put true? I meant to put true in quotes everywhere.
yeah, I know. That's right. But I mean, if you, in principle, if you took a huge ensemble which you couldn't afford having practically,
Right.
do research, you could create something for just research purposes to see what really should happen.
What do you think ensemble size should be for you to pass it through the...
10 to 7 or 10 to 14 members.
Does anyone have 10 to the 7 members in an ensemble?
Well, no, this is like a problem representing a full B matrix. It's exactly the same problem. If you had that size of ensemble, you would also...
Right, right. No, that...
It's equally impracticable to represent a full B matrix implicitly. It's just the same thing.
Yeah, I mean, a true estimate needs at least as many as degrees of freedom, but given that operationally, I don't think, actually it needs the same number plus 2. But operationally, I'm not going to get that many, but I'd be happy to have a number to shoot for. Our group thought 30 was great.
Well, if you have a good assumption as to what variables are uncorrelated, which I mean, the wavelets is a particular assumption about what variables are uncorrelated.
Well, no, there's another factor I'm not talking about, which is the balance transform.
Well, I was thinking just for if you just imagine that there's only one variable in the model, then you could say, well, it's variable harmonics are uncorrelated, or you could say wavelets
Right.
are uncorrelated, or you
Right.
could say grid points are uncorrelated. But
Exactly.
that's clearly wrong.
Exactly.
The other two are plausible.
Right, so the spherical harmonics, it would be plausible in the homogeneous case and not in the heterogeneous case. And the wavelets are compromised between grid points, which you'd need for heterogeneity, and spherical harmonics, which you need for scale separation.
Harmonics, if you would, from the uncorrelated and purely linear dynamics, which obviously you can do to A
Right.
grid plots, would never be plausible under anything you could think of. Wavelet is some ways trying to undo the biggest disadvantage of spherical harmonics to some extent.
Yep. That's more than fair. You could stand up here and explain it. That's a completely correct interpretation of why we're doing this and what we found. Because I'm very honest, I'm telling you that there are some fudge factors. So for example, for the recursive filters, there's a factor len underscore scaling. For the wavelets, the factor is just that L I talked about, which is the number of levels. Probably has the least fudge in it. And then there's another factor, alpha correlation scale. And I only roughly calibrated those for the purpose of comparison. And I'm not aware of a objective way to set those parameters. I think they were put there as a challenge to objectivity. And I just have one more, just for completeness, moving the observations point southward again. Again, seeing that the wavelets seem more close to the ensemble than the recursive filters. Okay, now some brief results about simulated representativeness error. Now, I like the Beamer class because you can see you're getting near the bottom. It's very encouraging. So on the top left here, actually the same data set, just one case though, showing outgoing long wave radiation. So that's my Y. It's again a map over longitude, latitude. Okay, now in the center, as I promised, I'm going to talk about how wavelet coefficients look. So this is the log base 10 of a wavelet coefficient plotted versus those indices I1, I2. And then the indices are in the log scale. And the tick marks are the I bar L for each level L from 0 to 10. And the horizontal resolution is N1, N2 is 951 by 882. So the I bars are decreasing roughly by half, but not always by half. And then what I want to call your attention to is that the distribution of wavelet coefficients forms these little patterns. You have to look very closely, but basically there are boxes of logarithmic dimensions which each contain some repetition at some scale of the full pattern. And boxes along the diagonal contain patterns which are more or less equally distributed north and south, and then off diagonal contains information about patterns which have aspect ratios. And then depending on the choice of L, in this case I chose the largest L, all of these patterns in each box are high pass coefficients, except for this big red box at the lowest scale, which is the overall mean of the data. And so that's the very typical way that wavelet coefficients look as an array. Notice this is log base 10, and this is the value, so there's quite a range in the magnitude of wavelet coefficients. The next to the right is the thresholding of the wavelet coefficients using the previously explained algorithm. So there are 536 which pass the threshold. That's 0.064% of the coefficients. Notice that most of them are at larger scales, but if you have sharp eyes, you can see that there are features also at intermediate scales which are significant by this threshold. So it's not merely like a band passing, but really magnitude selection. And because of the nature of wavelets, magnitude selection corresponds to basically information and spatial variance capturing. So I think my caption ran off the bottom, but the this part here is the reconstruction. So given those 536 wavelets out of the original 800,000 or so, the reconstruction is this. And depending on your fussiness, you might think this is a very good or very bad representation of the original outgoing long-wave radiation field. So now just a quick picture of what the thresholding was. The solid curves are the wavelet coefficients. The dashed curves are the Fourier coefficients, just for reference purposes, basically. The red is the observed. Green is the background, which is, for this experiment, is merely a a smoothing of the observation. Tom's application here is satellite observations, in which the satellite actually contains more information than the model does. So the background is merely a smooth of the observation, but using a different method. And then the blue is the O minus B, the difference of those. And so notice that since the background is smooth, the green always decays faster than the red, basically. And then this asterisk marks the point where the separation between the red and green curves starts to become significant. You would need to zoom in here to see it, but that's defensible, I think. I mean, I can defend it because I have zoomed in, but that's what the algorithm finds. So now we can reconstruct. The left is the difference, the O minus B, or the Y minus C on the left, and then after reconstruction, after thresholding, we have it on the right. So what's hopefully useful is that differences that have gone away by fiat, we declare those to be unrepresentative. They were due merely to the fact that the grids, if you like, or the model error. This is just a toy test from one piece of data. But if the algorithm is correct, then those differences are not representative. But the differences that remain down here would be representative and therefore useful. So that's the result trying that algorithm. That's absolutely true. So the idea is, since we don't know any other way, we're trying a way which seems plausible to separate the error into those two parts. Enjoy your ride. That's the last slide. So, summary. I hope I've convincingly argued that wavelets have a great potential for data assimilation applications based on their long history of use in related areas and in recent applications. There's a slide of further reading after this. Whoops. Whoa, that was interesting. Wow. I don't know what I hit, but oh wait, I hit that. There we go. So at NCAR in the M-cube division, we're using tensor product wavelets. Those allow any size of data, and they can serve the sum of squares to machine precision. Some wavelet transforms don't do that, so I put that in. There's a method called bandpass summation. There are methods where people just sort of do some funny filtering in Fourier space, and you don't necessarily get this property. To the extent that spatial variance is kind of a proxy for statistical variance, this property is very useful. Now our group has, well, we have implemented a new background error covariance matrix using wavelets in the horizontal control variable transform, and the pseudo-single observation tests are indicating an advantage in regard to representing heterogeneity and anisotropy. And we're starting to look at wavelet thresholding as a tool to address representativeness error. And there's some reading. And any further questions? Thank you for your attention.
Use this in combination with
Have I? No. Why would I?